Every dataset, every observation, holds a secret language within its numbers, a fundamental structure that dictates how likely certain events are to occur. This underlying blueprint is what we call a probability distribution, the very DNA of your data. Understanding these distributions isn't just academic, it's crucial for anyone working with data, especially in machine learning, to properly interpret, model, and predict. At its core, a probability distribution describes all the possible values a random variable can take and how often it's expected to occur. It tells us the likelihood of observing different outcomes. Think of it as a map showing the probability landscape of your data, revealing its shape, spread, and central tendencies. Let's begin with one of the simplest, the uniform distribution. Imagine a fair six-sided die. When you roll it, each outcome, 1, 2, 3, 4, 5, or 6, has an equal probability of occurring. That's a uniform distribution. Every value within a given range has the same likelihood, forming a flat, rectangular shape when visualized. There are no peaks or valleys, just an even playing field. In machine learning, the uniform distribution often appears in initialization schemes. For example, when you randomly initialize weights in a neural network, you might draw them from a uniform distribution to ensure no particular weight is favored at the start. It's also found in sampling techniques where you need to select elements with equal probability, or in simulations requiring truly random numbers within a bounded interval. Next, we have the binomial distribution, a discrete probability distribution that models the number of successes in a fixed number of independent trials. Each trial must have only two possible outcomes, success or failure, and the probability of success must remain constant for every trial. A classic example is flipping a coin 10 times and counting how many heads you get. In the realm of machine learning, the binomial distribution is fundamental to understanding binary classification problems. If your model predicts whether an email is spam or not, or if a customer will churn, each prediction can be seen as a Bernoulli trial. The aggregate performance over a batch of predictions, like the number of correct classifications out of a fixed set, often follows a binomial pattern. The Poisson distribution deals with the number of times an event occurs in a fixed interval of time or space, given that these events occur with a known constant mean rate and independently of the time since the last event. It's particularly useful for modeling rare events. Think about the number of customers arriving at a store in an hour, or the number of typos on a page. For machine learning, the Poisson distribution can model event counts. For instance, in natural language processing, it might describe the number of times a particular word appears in a document. In recommendation systems, it could model the number of clicks a user makes on certain types of content within a session. Its assumption of independent, rare events makes it valuable for specific counting scenarios. Now, let's turn our attention to the superstar of probability distributions, the Gaussian, or normal distribution. You've undoubtedly seen its iconic bell-shaped curve. This continuous distribution is characterized by its mean, which dictates its center, and its standard deviation, which determines its spread. It's perfectly symmetrical, with the mean, median, and mode all coinciding at the peak. Most data points cluster around the mean, with fewer occurrences as you move further away. The profound prevalence of the normal distribution is largely explained by the central limit theorem. This powerful theorem states that, under certain conditions, the sum or average of a large number of independent and identically distributed random variables will tend to be normally distributed, regardless of the original distribution of the individual variables. This is why natural phenomena, from human heights to measurement errors, often exhibit a normal distribution. In machine learning datasets, the Gaussian distribution appears everywhere. Many continuous features, like age, income, or sensor readings, often approximate a normal distribution. Preprocessing steps often aim to transform features to be more Gaussian-like because many algorithms assume normality for optimal performance. Understanding if your features are normally distributed helps you choose appropriate models and normalization techniques. Crucially, the Gaussian distribution is often assumed for model errors. In linear regression, for example, a key assumption is that the residuals, the differences between the actual and predicted values, are normally distributed. If model errors are Gaussian, it implies that the model's predictions are unbiased and efficient. Deviations from this assumption can indicate issues with the model or underlying data structure. Each distribution comes with its own set of assumptions. The binomial requires fixed trials and independent outcomes. Poisson assumes a constant average rate and independence of events. The normal distribution is often approximated due to the central limit theorem, but has strict mathematical properties. Understanding these assumptions is vital, as violating them can lead to flawed analyses or models that perform poorly. Recognizing which probability distribution best describes your data is like identifying the specific genetic code of your observations. It guides your statistical tests, informs your choice of machine learning algorithms, and ultimately empowers you to build more robust, accurate, and interpretable models. Dive deep into your data's DNA and unlock its true potential.